Welcome to another edition of Math for No Reason. In this edition, we'll first prove this inequality. Here we have four real numbers a, b, x, y with x and y both positive. Then we will show that a square by x plus b square by y must be greater than or equal to a plus b whole square divided by x plus y. And then we will use this inequality to give an alternate proof of the well-known Cauchy-Schwarz inequality. So let us first prove this result. Since x, y and x plus y are all positive, we multiply both sides by xy into x plus y to get a square into y into x plus y plus b square into x plus y greater than equal to a plus b whole square into xy. Now this is what is to be proved. So we have not proved it. We have just multiplied this result which we are trying to prove with xy into x plus y, which is greater than 0. Now simplifying. So opening up this, we get a square xy plus a square y square plus b square x square plus b square xy greater than equal to a square plus b square plus twice ab xy. A square xy cancels on both sides, b square xy also cancels on both sides. So we are left with a square y square plus b square x square greater than equal to 2ab. Now I will repeat that we have still not proved it. We have just expressed this inequality in an equivalent form. So we note that a square y square plus b square x square minus twice ab xy is ay minus bx whole square, and you know that that is always greater than equal to 0. So we have proved this result. And when will equality hold? Equality would hold if ay minus bx is equal to 0, that is y by b is equal to x by a. Equality holds if and only if ay minus bx is equal to 0, which implies y by b is equal to x by a. Now this is a very simple result, and now we will use this to prove the Cauchy-Schwarz inequality. But Cauchy-Schwarz inequality involves n numbers. So first let us see if we can generalize this. Now if we have three numbers, a square by x plus b square by y plus c square by z, then applying the inequality on these first two terms, we get this is a plus b whole square divided by x plus y plus c square by z. And now again using this inequality, we get this is as a plus b plus c whole square divided by x plus y plus. And now we can apply induction to get a far more general result. A1 square by x1 plus a2 square by x2 plus an square by xn is greater than equal to a1 plus a2 plus an whole square divided by x1 plus x2 plus xn. Of course, here we are assuming that x1, x2, xn are all strictly positive. So if x1, x2, xn are strictly positive and a1, a2, an are real numbers, then a1 square by x1 plus a2 square by x2 plus an square by xn is greater than equal to a1 plus a2 plus plus an whole square divided by x1 plus x2 plus plus x. So this is the result that we will use to prove the Cauchy-Schwarz. So let us recall that the Cauchy-Schwarz inequality has the form that a1 square plus a2 square plus an square into b1 square plus b2 square plus bn square is greater than equal to a1 b1 plus a2 b2 plus plus an bn whole square. So this is the Cauchy-Schwarz inequality, and we'll have to prove this. Before starting the proof, also let us note from what we had done earlier that equality would hold in this inequality if a1 by x1 is equal to a2 by x2 equal to an by xn. Now let us begin with a1 square plus a2 square plus an square, and we write this as a1 square into b1 square divided by b1 square plus a2 square into b2 square divided by b2 square, etc. an square into bn square divided by bn square. So note that b1 square, b2 square, bn square are all positive. So this requirement that x1, x2, xn are all positive is met here. So in this inequality, we are seeing that the role of a1 square is being played by a1 square, b1 square. The role of x1 is being played by b1, and similarly for the other term. So this is greater than equal to a1 b1 plus a2 b2 plus an bn whole square divided by b1 square plus b2 square plus bn. So this result comes from this inequality. So clearly we see that just bringing b1 square, b2 square plus bn square on the left hand side, we get the Cauchy-Schwarz inequality. And the condition for equality also follows from this. Remember that the role of a1 is being played by a1 b1 here, and the role of x1 is being played by b1 square here, and similarly for all other terms. And this gives us the condition that equality holds if and only if the two sets of numbers are proportional. So we've been able to provide a simple alternative proof of the Cauchy-Schwarz inequality. Thank you.